Good day. We are tackling our case study titled Faults and Defects in Power Transformers. We are Gavino, Gualter, Magnaye, Morados, Pasco, and Kaibigan. Introduction. Power transformers play a vital role in the electrical power industry by efficiently transmitting electricity between different voltage levels. However, like any complex electrical device, transformers are susceptible to faults and defects that can compromise their performance and reliability. This case study presents an in-depth analysis of a real-world scenario involving the identification, diagnosis, and the mitigation of faults and defects in a power transformers. Problems: stoppage in the electric power system due to transformer defects and faults.
Issues. The case study analyzed the service stoppages of power transformers over a period of 28 years, from December 1979 to May 2007. A total of 549 service stoppages were recorded, involving 255 three-phase transformers or transformer banks. Some devices experienced multiple stoppages during this period. The study considered both devices that were permanently removed from operation and those that were newly purchased during the study period. It is estimated that 10% of the damages studied are part of the overall number of transformers that form the technical reserve of the system throughout these 28 years. The study revealed that most affected components in power transformers were windings, which is 34%, bushings, 14%, on-load tap changers, OLTC, 10%, and the energized tap changers, DTC, 10%. The category of unidentified component, 11%, referred to components for which reliable records were lacking due to various reasons. The insulation system of the transformers consisted primarily of oil paper insulation, although solid insulation materials are like cellulose, varnish, or polyester were also present. It was observed that stoppages solely attributed to problems in the insulation oil accounted for only 4% of the total number of stoppages during the 28-year analysis period. The study emphasized that the aging of both insulation paper and oil affects the life expectancy of a transformer. By continuously monitoring and controlling factors that contribute to insulation degradation, such as the condition of the oil and environmental parameters, the risk of electrical faults can be reduced, ensuring the reliability and longevity of our transformers.
Number 3. Transformer failure rates over time. The studies distinguish between defects and faults as causes of service stoppage in power transformers. Defects can be addressed through planned inventions, while faults often arise as emergencies in the electrical sector. Therefore, it is crucial to understand the individual failure rates of transformers. The study highlights the distinction between defects and faults as causes of service stoppage in power transformers. The failure rates of different voltage classes were analyzed, with slightly higher rates observed for 138 kV and 230 kV transformers due to their smaller numbers. CELG's low failure rates are attributed to the implementation of predictive techniques, including the detection of partial discharges using the acoustic method. These efforts aim to minimize failures and maintain a reliable power supply. Analysis of the issues. So first is the laboratory testing. So to dig deeper into the nature of the faults, several laboratory tests were performed on the failed transformers. These tests included dissolved gas analysis or DGA, oil, di- oil dielectric strength testing, and insulation resistance measurement. DGA helped identify the presence and type of gases in the transformer oil, which can indicate specific fault types such as overheating, partial discharging, and arcing.
Core and windings analysis. Further analysis involved inspecting the transformer, core and windings. Core faults such as core insulation failure were examined using techniques like core loss measurements and transformers. Turn ratio tests. Windings faults include short circuits and open circuits. Were investigated through insulation resistance testings and winding resistance measurement. Next is the failure root cause analysis. Based on the data collect and analyze, the team identified several root causes contributing to the transformer failures. This includes first is the overloading. The transformers were operating close to their rated capacity due to increased load demand, leading to excessive heat generation and accelerating aging. Second is contamination. Presence of moisture, dirt, and conducting particles in the transformer oil, leading to insulation breakdown and reduced dielectric strength. Letter C is insulation of degradation. Age-related degradation of insulation materials, such as paper and varnish, resulting in reduced dielectric properties and increased risk of short circuits. And the last is the poor maintenance practices. Inadequate or irregular maintenance activities, including oil sampling, testing, and servicing, which resulted in undetected faults and improper remedial measures.
Next is the failure root cause analysis. Strategies to address the identified issues and prevent future failures. The following mitigation strategies were implemented. A. Load management. The power distribution company optimized the load distribution among the transformer and implement load shedding measures during peak demand period to avoid overloading. B. Oil filtration and purification. A comprehensive oil filtration and purification system was installed to remove containment and maintain the dielectric strength of the transformer, all within the acceptable limit. C. Improved maintenance practice. The company established a rigorous maintenance schedule that include regular oil sampling and testing, as well as preventing measures like cleaning, tightening connection, and replacing aged insulation. And D. Condition monitoring. Advanced monitoring systems such as online DGA monitoring and temperature sensor were deployed to detect early sign of fault and deviation in transformer performance. Comment on effective solution and strategies. Power transformer experience various stresses during operation, leading to the degradation of oil paper insulation system through paper decomposition and oil oxidation. This degradation compromise the insulation quality and partial discharges, cause further damage and accelerate aging of the transformer. Detecting PD serve as a crucial measurement for online monitoring and building an early warning system. Next is the systematic equipment monitoring using the DGA technique shown in slight increase in gases indicate potential issues. However, it did not provide a clear warning to remove the device from service, which eventually led to damage to short circuit between the winding spirals.
For the comments on effective solutions or strategies, the scenario could have been avoided through the detection of PDs, which have prevented the defect from progressing into a short circuit and subsequent equipment failure. So the study highlights the importance of the integrating predictive maintenance techniques to enhance the diagnostic quality of assess the state of the transformer insulation systems. So the paper proposed an improvement in the predictive techniques by combining DGA with the detective of PDs using the acoustic emissions method. This integrated approach allows for pinpointing PD activity within the equipment without requiring its shutdown, providing a more comprehensive and effective monitoring solution. So, for the conclusion, the study highlights the importance of proactive monitoring, timely maintenance, and proper mitigation strategies to prevent faults and effects in the power transformers. So, by investigation or the investigating the root cause and implementing effective measures, so the power distribution company successfully minimized. That's all. Thank you.